was a PhD student at UCLIC many years ago, joining in 2009, 2008, and finished in 2012. Can you see my video, by the way? So this is, can anyone see this? I'm not sure. But I've, as you can see, we've not only got a virtual time machine now, so we've gone back in time to the office in which we used to have our supervision meetings back in the day in the old UCLIC space. I thought this was a bit of a walk down memory lane. So, you know, for the new virtual format, we can now do time travel as well. So obviously, since finishing his PhD at UCLIC in 2012, Chris then went over to San Francisco to a postdoc at Smith Kettlewell, and then returned to the Netherlands, where he took a faculty position at Utrecht University and has been there for a number of years. And I will hand over to him to let him speak about what he's currently up to. Looking forward to your talk, Chris. Thanks for coming all this way to London.
I need to unmute myself. Great, thanks for inviting me. And let's see if I can get the technology to work. There we go. It's a pleasure to be at UCL virtually and to talk with you. And the train ticket company actually didn't want to reimburse me for my ticket, but they said you can rebook it. So at some point, I'll hopefully be physically in London and we can also catch up that way. Today, I'm going to talk about some of the research I've been doing over the past couple of years, which is about interruptions in our use of automated devices. And I hope I don't need to convince too many of you of this, but one of my main aims will be to convince you that it's an exciting time to think about human behavior in human automation interaction. And I think it's important that we think about human interaction. So for the trip down memory lane, I also brought a picture of UCLIC almost 10 years ago. This is Sandy, I saw us in the audience, is also in this picture. And 10 years ago was a very exciting time for HCI, I think. And one of the reasons was that lots of new technology was being released. So there were smartphones, tablets, games with tracking ability like the Kinect, lots of wearables. And the exciting part for HCI was to explore the full potential of these technologies. What can we actually technically do with it? But today is also an exciting time for HCI, but for different reasons. And it's because not just the technology is at the forefront, but the human even more so. And we recently wrote about it with Duncan as one of the co-authors, and also Stella Donker, my colleague from Utrecht, and Andrew Kuhn from the University of New Hampshire. We did a review of the literature in the International Journal of Human-Computer Studies on automation and human automation interaction over the past 50 years. And this is my main way of summarizing where things went. This is roughly a Venn diagram. So within those 50 years, almost every year, there have been publications about automation. So it's really nothing new. However, the focus has slightly shifted and expanded. So originally, we were mostly thinking about things like expert systems, very controlled domains where we wanted to understand how to inform humans through automated inferences. Now that's expanded slightly to, for example, safety critical domains like power plants, where the automated technology was used by professional users in a more complicated context, but incorrect use of the technology might have led to accidents. So these were used by very well-trained professionals. Fast forward to the more recent years, and lots of non-professional users, including myself, are using non-automated tasks. One of the exciting things in my life is that 2 years ago, I got a dog. The dog sheds, so, oh, actually, that's my next example. We got a robot vacuum. And that's an example of me as a non-professional user using an automated system. It's definitely not safety critical unless the dog is in the way, but the vacuum actually runs while I'm outside with the dog. Other things that we encounter are, for example, online chatbots. Almost every big company has a person with whom you can talk if you go to their website. I'm not convinced these are all persons, but you are first being filtered by a chatbot. There's also overlap of non-professional users, so all of us that use automated systems in safety critical settings. For example, lots of personal medicine applications are around, and a lot of you at UCL know a lot more about this than I do, so I will not go into too much detail there. A fourth area that's emerged is that these automated technologies are more and more in embodied situated systems. So you see here 3 examples. Again, my robot vacuum is one of the examples. On the safety critical end, you might think of military drones, for example, which are being used by professional users in safety critical environments. And what is important about these embodied situated systems is that these are robots that are out there in the world and they interact with the environment, and actually their interaction with the environment shapes what the robot learns or what the robot does. It's not just pre-programmed and doing something like you might think of in a factory, but it's actually this interaction that drives the behavior. Now, right here in the middle is a domain that I care about a lot, automated vehicles. And it's not just an interesting domain because automated vehicles are interesting of themselves, but it's also an interesting example domain because all of these things come together. So it's an automated system. It's being used by non-professional users because the drivers of cars have their driver's license, but they don't have an automation license. And they're being used in safety critical settings, namely driving. If you respond too late to an alert, you might get into a car crash. So in a nutshell, what we've seen is that automated systems the use of them has really expanded over the last 50 years into more and more domains with a wider variety of users. And therefore, I think, apart from the global pandemic that we're facing, this decade is really an exciting and critical time for HCI because the full breadth of HCI can be applied to this. Because we're not just concerned about the technological innovations that are out there, but it's even more human-centered. The human is really central in our understanding. And in the paper that describes this work, we discuss a couple of emerging trends. And one of these emerging trends is that there's now really a need for interdisciplinarity and breadth. So given that a wider set of users are using automated technology, given that they're being applied in a wider set of domains, and given that, including safety critical, and given that these automations are embodied systems that are physically out there in the world, we really need to understand a lot about them. So we need to think about how do we actually train these non-professional users? Might they use some skills? What might be cultural differences or differences in norms or customs or conventions? How can we accommodate for that in the technology that's being used? And how can we make the full use of the wide set of methods that we know from human-computer interaction, but also the social sciences, philosophy, linguistics? How can those really move the field forward? And here, I think for all of these questions, I don't have the answers. I have a lot of questions about them. But I think it's really a call to arms that all of us can contribute to this. And no one person can know everything because the environments are getting so complex to study that we really need to benefit from each other. Another emerging theme, it has to do with regulation and explainability. And I put the European flag here because I think the EU as a government organization has been really a pushing force here, in the sense that the General Data Protection Regulation has been released, and I'm not sure whether some of you encounter this, but it's quite complicated to keep track of all the administration. But one nice thing here is that it includes a right to explanation. So if people use automated systems and the automated system makes a decision for them, for example, whether you are allowed to get a mortgage, you have a right to an explanation. So this has really pushed forward this idea of explainable AI. It's really required by law now that our AI systems can explain why they reached certain decisions. And this is exciting and placing the human first, because it's not just focused on designing the black box, but it's about being able to explain what that black box came up against. So, and making sure that it's beneficial for humans, that having us think about biases that might be in these systems, for example. There's a lot of other emerging themes. I won't discuss them in detail, but there's of course lots of ethical and social dilemmas. Again, the human is placed first there. Think about job security, moral decisions that sometimes these systems might be involved in. A human and humane experience. So if automation takes over certain tasks, are there perhaps tasks that we would like humans to do, not because it's necessary, but because it's fun or it's a human experience? Arts, creativity. how can we ensure that that remains used? And of course, there can be radical changes. I am very bad at predicting radical changes, I know from myself, but there will definitely be more developments that we don't anticipate now. And now you might think, okay, so everything is new because this is all very radical and new. But of course, there have been themes around for these 5 decades on research. And despite that they've been around for so long, we still don't have the answers, and there's still an urgency in addressing them. So here are a couple of examples. Function and task allocation is one example. So if automation takes over certain tasks, but humans are also involved in them, say they share the control of a car, how do we allocate specific tasks or specific functions to either the machine or the human? And the reason that this evergreen theme is still around is because we've come to appreciate that machines and humans are not static. So there used to be ideas like machines are good at this, humans are good at other things, creativity or sensor processing. And I think there's more and more appreciation that both machines and humans actually develop these skills. Brings us also to like trust, incorrect use, confusion. Given that these machines are taking care of all kinds of tasks, how can we make sure that we use them in the correct way, not over rely on the machine, but actually collaborate? And that involves some management of attention. So if some tasks are being done by the machine and some by the human, how do you go back and forth? And this last item is one that's of particular interest to me, and it brings on to the second part of the talk, because one idea that I've been really entertaining and that I hope interests a lot of you at UCL is this idea that in our use of automation, for example, cars, that we can use the perspective from interruption theory and interleaving. And we wrote a paper about that last year that I'd like to walk you through. So we're going to look a bit more in detail at cars. There's many reasons for motivating automated vehicles, and it depends on who you ask and where you ask that what the reason is. But one of the motivators is that there's an estimate that in 90% of the traffic accidents, there's some human factor involved in that accident. So we might be a bit drowsy, we might have emotional behavior, road rage, we might be distracted by our phones or by conversations. So the idea that engineering put forward is, well, okay, the human is clearly not good enough. What if the car just drives by itself? And there's many prototypes of what these cars might look like. I tried to find a public shareable picture. I think this is a Mercedes example. Notice here how if you were to be seated in this car, which clearly is not on the road, but imagine it would be on the road, you would face each other and you would not control the steering wheel. So maybe this is a case closed, right? No human behind the wheel, no human in control, everything will be fine. Unfortunately, it's not a case closed, because this is really talking about full automation, and full automation is not yet commercially available. And there's all kinds of gradations of automation in between, from no automation, which is your conventional vehicle as most of us know it today, to some of these systems where there's partial automation. So an example is the Tesla Model S that you see here, where you might be driving, but occasionally the car might be driving, but occasionally the car might run into a situation that it cannot handle, and you might have to grab the wheel and it will alert you on how to do it. And this is really where the action is at the moment for research on automated vehicles. So these situations of shared control, where sometimes the car does some tasks for you, like a Tesla can help you with staying in the lane and staying at an appropriate distance of the car in front of you, but you have to make sure that you obey all traffic laws, for example. In such situations, there might be occasional transitions where the car is taking care of a task and you take over. And the very much simplified engineering perspective might be that at such a point you play an alert and a human response. And the effort that we want to try to make sure is that the time between the alert and you taking control is minimized. However, the human model behind this sort of assumes that people are like my PhD student that you see here in this picture, and they are paying full attention, right? He is, I asked him to do so because I was a passenger, but he is paying full attention to the road, and he has his hands close to the steering wheel that if there's an alert, he can immediately grab it. But I think most of us have encountered situations through which we know that this is not exactly how our human attention works, right? This is more like how our attention works. If some task is being taken over by a machine, the car is driving itself, we might want to check our cell phone or do some other task. Human attention is limited and humans get distracted. This is not to say that this is something we want, but it's definitely something that we've observed in the real world. So it's something that our models of how humans might use this technology should account for. And in that engineering perspective, it's not necessarily there. There have, of course, been studies where people consider the human factor, but the call to arms here is really to look at it even more detailed. And the interruption perspective then is to explicitly acknowledge that there might be more than one task. So the car might be driving, maybe in an automated function, and while it's doing that, you might be doing some other task like checking your phone. At a certain point, the car might run into a situation where it cannot finish the driving, and it might issue an alert to trigger you to assist the car. Now, in that case, the human transition might not be an immediate task switch. You might not immediately grab the wheel because you know that the technology can handle it a little bit. And you might also be very engaged in a task that you've prioritized, right? Definitely in cases where the automation is getting better and better, situations where the humans need to take over will become more of the exception. They will be irregular. So you might have been accustomed to doing other things. So what we anticipate is that there will be more interleaving, going back and forth. So you might look up from the task that you were doing, orient to the road, see if immediate action is needed. If not, you might want to spend your time on first finishing the original task, or at least coming to a more natural breakpoint. And the psychological literature and the HEI literature suggests that there's all kinds of advantages to finish off first a little bit of where you were so you get into a better mental space to take over a more challenging task like driving. So by spending some time on interleaving, you are in a better position to grab the wheel. Then after you've grabbed it, at a certain time, hopefully you are beyond this situation where the car needed assistance and you can return again to your original task. And some interleaving might be necessary, at least in situations where I use some of the automated functions in my car. The first moment that I turn on that automated function, I'm a bit of a control freak, so I don't immediately trust the car. So I want to check what's going on. So a little bit of interleaving might be going on here again, where you first check, okay, is the car really doing what I want it to do? And you might orient again to your original task. Now, if you align this with interruption models, then you might identify 10 stages. And I won't go into all those 10 stages in detail, but if you're very interested in them, then in the paper we've described for each of those stages roughly what we think is known and how that might inform design and future research. But why would you want to consider this interruption perspective? Well, first of all, I think it's a more realistic perspective of human actual behavior. It makes very explicit that this transition of control is not just one event, as it's sometimes described in the wider set of literature. Instead, it's a series of stages that you go through. Moreover, it makes very explicit that we are not always paying full attention to the driving task, but we are also doing other things. And therefore, that model helps us to think about how can we accommodate such attention switching, not as something that we should encourage, but as something that as designers of technology or evaluators of technology, we should take into account. And recognizing those different stages allows all kinds of things. So it allows for alignment with theory about these specific stages. And it also allows for targeted intervention. So rather than saying you are going to make an intervention for transitions of control, you can say you want to address specifically the problem of helping a human to orient to the road, to the driving environment, or you want to help them with disengaging from their original task. So it adds a little bit to our vocabulary and precision. Moreover, you can then also explicitly study, if you were to optimize a specific stage, how might that impact the other stages? So for example, if you optimize in your design for a quick transition from the automated vehicle to the human, how might that impact the later stages once you return control to the car and you resume it again? And again, there are predictions from the interruption literature about how those, how there might be interactions between trade-offs between speed and accuracy. And I know that some of you are also very familiar with this work. So that's been a little bit abstract. So I want to make it a little bit concrete, but at the same time, with the limited amount of time, not go into too much detail. But I want to go into two specific studies that my PhD student Remo has conducted. This is him here. This is a headshot at Kai. If the PhD students, if you're ever at Kai, there are very cool professional photographers. Remo's about to defend his thesis. So Duncan's going to be an academic granddad as of June 5th. And Remo's research has been on auditory alerts in driving and how susceptible people are to those alerts. And I want to look at two studies that focus on specific stages. The first at stage 1, how the brain actually processes alerts, and then at the interleaving process in the beginning. So let's first look at this stage. So if you're in an automated vehicle like this, there might be all kinds of sounds, and some might be constant and you might filter them out. And normally I would have sound examples here, but they are really loud. So I took them out, but this might be a simple beep, right? So your occasional beep, beep. Sometimes there are slightly deviant sounds that look a little bit like what you've heard, but they're slightly different. And sometimes there's very unexpected sounds, like maybe a dog barking or a sneeze or a kid running behind a ball. Now, the way I've described this, it very much aligns with a paradigm that we know from psychology, which is an oddball paradigm in which people are presented with frequent tones, but occasionally there are novel sounds that are distinct from these tones. And what we can do in the lab is we can put people in a driving simulator. This is the setup I have in Utrecht. We can put up an EEG cap and we can measure the electrical activity in the brain. Let's see if this video clip works. Not sure if you heard the sound with this video clip, but there's a very frequent beep. And occasionally there's a very different sound. I think the first one was a bit like a seal. There was another one. Now what we can do with such a setup is we can measure what the electrical activity is in the brain when you hear these beeps, and we can measure what the activity is when we hear these other sounds, these novels. And then we can create a difference wave. So we can see what's the difference, what's the added activity if you hear a very unexpected sound compared to something expected. If you are doing nothing at all, you're just sitting there, there's a blank screen in front of you, then we see that in frontal regions of the brain, there's added activity when you hear something unexpected. And the idea is that this added activity has to do with a behavioral interrupt. So you hear something novel and you are orienting, what should I do? Now, if people are placed under automated driving conditions, then this signal is reduced a lot. And we found that quite consistently in multiple studies. So the layman's conclusion, there's more detailed graphs if you're into that, but the brain is less good at processing these auditory alerts during automated driving. And I think that is a little bit of a problem because automated driving, of course, relies on these alerts. So in a situation where you should be extra susceptible to alerts, you are less susceptible. And of course, the sounds that we used in these experiments, they are very artificial. They are nothing like an ideal alert, but they do give some insight into this general ability of the brain. So as a second example, I want to look at a more applied study. This is work that Remo did while he was interning at Microsoft with Shamsi Iqbal. And this looks at designing for effective transitions of control. And it's really about this series of stages in the beginning. And you could say the idea is that because we might miss an occasional initial alert, why don't we warn a bit longer? And also, given that people might want to interleave a little bit and might want to go back and forth between checking their original task, orienting to the new task before they really give up on their original task, we should give them a bit more time to do that. So here's a video clip where you see the setup. This has sound, I hope it works, but you will hear a series of beeps that gets progressively more frequent.
Automation disabled.
So what you saw here, and I hope that you also heard, is that there was a progressive series of tones, and you could see that the fog was getting thicker. But before it was really thick and it was dangerous, and maybe in the real world context, the sensors of the car might not work fully. The user was already alerted, so they could pay attention to what was going on the road. They could have their hands ready. And this has a lot of benefits. So one idea is that it allows to finish this non-driving task at a more natural breakpoint. And those that know what I've been working on also with Duncan, this is something that interests me a lot. So what are efficient positions in the task structure to finish something or to orient to a new task? It also allows drivers to look earlier at the roads. So the behavioral data shows that drivers look up earlier, orient to the road. So actually before their action is critical, they have some time to orient, okay, what is actually the right thing to do, instead of hearing alert, grab the wheel, and you need to do something, but you are completely flabbergasted about what's going on. And we then also saw that they handled these emergency situations slightly better. So for example, if you had to press the brake, if you hadn't had that pre-alert and there was just a last minute alert, take control now, then people were a bit delayed in their response and they pressed the brake really hard, which might not always be safe if there's cars behind you. But in the situation where there was the pre-alert, they pressed the brake earlier, but were also able to press more gradually, so they came to a more careful stop, which has advantages. It's often safer. So I've really described studies about specific stages. And the thing is that it's really hard to study all of these stages at the same time, right? So we're trying to make targeted interventions. But there are a couple of exciting things at the moment where we are looking more at the bigger picture. So Divya, I'm not sure if she is in the call today. She's a PhD student with Andrew Kuhn, and she recently shared a very exciting data set where she looked at how people go through these different stages. And the data actually shows that if you give people opportunity to interleave, if there's really a good pre-alert, a good forewarning, that indeed the stages that people go through align very well with what the interruption literature would predict. Whereas if there's a last minute alert, it's more of a case of, okay, let's drop everything we were doing, grab the wheel, might not always be safe. So she still has to write that up, but I'm very excited about that data set already. Then I have a virtual intern. This is something that's happening now with the COVID-19. There's a student from the University of Groningen who was there also working with Jelmer Borst, who was planning to intern with me, but he never made it to Utrecht. So instead of collecting empirical data, we're now making a process model that simulates these various stages. And the idea is that there's lots of literature about individual stages, either driving literature or more general literature. And you can look at, well, what is the distribution of times that we've observed in the literature for different stages? And with these simulation models, we are now combining them to see how do those distributions then shift, or what is the distribution for the entire process what might be the fastest that someone might respond and what might be the slowest. And what we're planning to do is to also look at differentiations between different alert types. So I hope something cool will come out of this, but we'll need the summer to look into it a bit more. So to conclude, I want to return to this original message. I really think that the way that human automation interaction is now being handled in science, but also in society and also at a governmental level, it's really an exciting and critical time for human-computer interaction, because automation is being used more widely in more domains by a wider variety of users. And therefore, we really need to understand that wide variety, and we really need the expertise of the wider HCI community. There's also a need and a governmental push to really understand human interaction. There's a lot of the EU agenda on AI also included human-centered very explicitly in their pitch. Now, in the end, there's a lot of engineering behind it, but I do like that they understand at the highest level that we do need to think about humans. I think there's also an understanding that automated technology is not just a solution, right? It's part of the equation. We really need to think about automation and humans. And I think that this interruption perspective is useful because it allows some alignment with the social sciences and targeted interventions for specific stages. And I've mentioned some concrete studies. So this idea that the brain might not be as susceptible to alerts as we might want to, and the benefits of early warnings. Now, before fully going over to the questions, I have one anecdote that I think is funny to share. So in October, I was invited at a conference in Shanghai. And while I was there, I visited the Auto Expo. And there's a larger context that's interesting about this, but we could talk about that in the Mozilla Hubs. But within this museum, I ran into this car. And this is the Oldsmobile. And it's one of the first non-horse-driven cars. It's from 1904. And it had a very interesting advertisement sign behind it. And here's the sign, and it reads, "Nature made a mistake in giving the horse brains. Science did better and made the Oldsmobile. Mechanically perfect and presupposing brain in its owner. I wonder why." So I think in 1904, of course, they were steering it towards the technology, but I think there's something here, like not every technology is perfect. Not every animal is perfect. So you really want to trust human brains as well. So you want to use both the technology and the human brain. And now, 100 years later, that we're making another transition from human brains to really mechanical brains, let's keep in mind that it's good to look at both. With that, I hope I convinced you a little bit that it's interesting to look at human behavior and human automation interaction settings. Thanks again for the invite, and I really look forward to your questions. Thanks.